Hello and welcome to Toddcast number 43, continuing on alkene addition reactions. So we've gone into Markovnikov versus anti-Markovnikov, mostly Markovnikov examples, potential for rearrangement when we use an acidic condition uh, or reaction condition. We've also gone into oxymercuration to form a addition hydration reaction, an alcohol from an alkene but not have to deal with rearrangement. So I want to continue on that and just add a few more reactions to our overall pool of information. So wanted to kind of pick up or just what we did in Toddcast number 42 that matters. And we considered this reaction, this mercury acetate, and again, want to emphasize that the plus charge and erasing it and putting it on the Hg over here, because it has a positive, it comes over, it coordinates, and coordinating, it prevents rearrangement, you get this. But I want to emphasize something this time. The water, if you show in the mechanism, came in from the backside and doing so attacked, broke the coordinated Hg bond, if you recall from the previous mechanism, and added OH. But we have freedom to do other types of reactions. So your job as a student when you study this is to not get locked into exactly what we show here. So for whatever reason, some reaction conditions, they might decide to make mercury with an oxygen and maybe instead of acetate, some other group, maybe a carbonate or something, possibly. Or instead of using water to put OH on there, they might use instead methanol to put, again, the H left here to go with the OAC, leaving an OH. So if the H leaves here to go with the OAC, you have OCH3 instead of an OH. So minor changes. The nature of chemistry is if you know the reaction in general, you can start making small changes to it to get the results you want. You change the conditions, the reactant, the solvent, whatever you want to change to exploit the reaction in a way that gets you the product you're aiming for. Okay, so just like we did with water, we're adding methanol. It's still a Markovnikov addition. The OCH3 is going to the more substituted. Ultimately, the H is on the less substituted. H goes where H is. And if we do it with methanol, what the heck we do with ethanol? So ETOH, again, the same story. The H of ethanol is going to combine with one of the OACs. Only one of the OACs is going on with the mercury. So the second one is going to combine with the H. ETO, the ethoxy group, is going to be added instead of the OH or the methanol, the methoxy group. Okay, so big picture. Know the mechanism really well for the simple case, and then by knowing the mechanism, realize what changes can we make. So the mercury species, not really much you can change because you want something to act like an H plus and be attacked, so it has to have a positive, which means it's a metal, but it has to be rich enough in electrons to coordinate, send some of its electrons back over to coordinate the carbocation that forms as the intermediate. Okay, so let's look at this in more depth. Want to consider that one being Markovnikov. Want to consider anti-Markovnikov for a minute and how that would happen. So this reaction, known as hydroboration, involves a BH3. So let's start with knowing that boron has an electron configuration of 1s2 in internal shell, 2s2, 2p1. So that's my valence shell. My core electrons are here. It only has 3 valence electrons, which means it has H, H, and H, and what's referred to as an empty p orbital. Empty p orbitals can receive electron density, so it ends up, this double bond can donate its electron density to the empty p orbital, and in doing so, make coordinated bond to boron, just like we saw with the previous mercuration, oxymercuration. You can reduce it to get rid of the mercury. Here you can actually do the opposite. You can oxidize the boron to get rid of the boron from the carbon and replace it with an H or in this case, an OH, excuse me. Okay, so just big picture. Let's just keep track of where everything is. So I have these two bonds, they're here and here. These two carbons of double bond are here and here. I have my ethyl group check. I have an H that's on there, so that must be this one. So the original groups here, 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 and then H are here, 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 and there's that H. So we've added the H and the OH and have emphasized that they're both down or they're both up. So I want to point out this is syn addition, meaning they're adding synonymously. They're adding to the same side at the same time. So that's going to be important when we look at that in the mechanism. Last thing I want to point out, there are three here because boron has three H's. Because it has three H's, that means it can react with three alkenes and ultimately lose the H when it gets oxidized. So hopefully it'll make sense when we do the mechanism, but it's a 3-to-1 ratio. And depending on if we get it just right, maybe a little too much alkene, too little alkene, we'll see what effect it can have. But the key thing, the OH is actually going on the less hindered carbon this time. So H is going to the one with less H's. No H's here, one H here. The H I've added is going to the side with no H's. So it's anti-Markovnikov in terms of regioselectivity and syn addition in terms of stereo chemistry, stereoselectivity. So because they add simultaneously, the BH2 that remains will go on one side, the H will go on the other. BH2 now is going to choose the less crowded side. So because the B is going on first, or it's going on simultaneously with the H, but it's the one that's bigger and controlling by accepted electron density, it will form on the less crowded side. And because they go on at the same time, they add syn. And then in the second step, the OH is going to displace the boron and move to the more crowded. So this is going to have a boron at first when I do the first step, but that boron is going to quickly be replaced by the OH of the peroxide. And in doing so, you're going to end up with an OH on the less hindered, the anti-Markovnikov carbon. Okay, mechanism time. Have to consider the mechanism. So let me go ahead and get rid of my drawing up here, where I click over. Regioselectivity, anti-Markovnikov. Stereoselectivity, I actually have some now. Syn addition. So anti-Markovnikov, OH goes on less hindered carbon. Syn addition, the H and the OH end up on the same side, either both on bottom or both on top. This gets repeated 2 more times because there are 3 H's total. So first one goes on, second one's going on, third one goes on. So the mechanism. This is where I really want to pay close attention. H and BH2 are going to ultimately interact here. And if I do this in the right environment, then I can simply have these pi electrons come here and attack the boron. That's going to happen. It's going to coordinate, and this H is going to move over. So for a brief moment, we represent it by dashed lines, meaning partially bonded. So there's partially a double bond here, partially a bond to H, partially to boron, partially a bond to H from boron, and the H is partially bonded to the carbon. So they're going to go on and eventually move into this scenario. So I'm going to end up with a BH2 on there. Okay, this is important. Once you have this R group on there, BH2 just went from being a very small molecule, 3 atoms or 3 H atoms and a boron in the middle, to now boron with 2 H's and a big group. This group just got bigger and bigger. So when it happens 2 more times, it now becomes more selective. So what we mean by this is the boron is going to go to the less crowded, H is going to go to the more crowded. But because BH2 and H aren't that different in size, 3 atoms compared to 1 is different, but it's not substantial. It could go the other way. B could go to the more crowded and H go less crowded, and it will happen on the first addition. But because this molecule for the second addition is so much bigger because you already have 1 alkene added, it rarely is going to choose the Markovnikov. You're going to get almost exclusively anti-Markovnikov in the second edition, and absolutely positively exclusively anti-Markovnikov for the third addition. So I want to take a pit stop and say that if I added one alkene plus one BH3, you're going to get about 80% Markovnikov. Timeout. 80% anti-Markovnikov and 20% Markovnikov. And I toss it out there. I don't know the temperature, so this is why I say about. If I were to add two alkenes, this is going to go up substantially to now around 90 and 10. If I had three, you're going to probably see it around 95 to 5 or even more extreme. So I want to emphasize that every time it goes on, it gets more crowded and therefore it gets more regioselective. Okay, that's an important point to understand this reaction is that it's a progressive reaction. There's three H's, so it goes on three times. First time, it's going to select anti-Markovnikov slightly more than Markovnikov, but each additional one is going to make it even more selective. Okay, and again, those numbers were just tossed out there. Okay, the peroxide. The second step, I want to emphasize that we are adding NaOH base and peroxide, HOH, which is going to turn into H2O, Na plus, and OOH minus. This OOH minus is now going to attack the boron. And again, boron has an empty p orbital and it loves oxygen, so that O is going to go on. So now the boron is going to carry a negative charge. I've turned these alkyl groups into just R's, just because it'd be way too much to draw. Oxygen and boron form a very strong bond. Boron loves that bond. So what can happen then is a boron can choose to keep the bond to oxygen and give up the R. So this is going to be very bizarre. How the heck could this ever happen reaction that actually happens? So this R migrates over, kind of like a rearrangement, takes that negative charge with it and adds to the O and kicks out that OH group. So whatever side the B is on, the orbitals have to stay on the same side. So if I were to redraw this, I'll have my R here, my R here, my boron, my oxygen to this other one. But now this boron has gone in the same, or the R group that was on the boron has gone in the same way on the O. And then this has left, so that bond isn't there at all. And I now have my negative charge on this OH. So I tried to leave everything in the same spot. But the key thing, this R, when it migrates over, stays on the same side. So whatever stereochemistry it has with respect to the B, it's going to have the same stereochemistry with respect to the O. So it was syn addition in the first step, so retains the results of the syn addition on the second step. Okay, so now we have this structure right here. This is free to go off, and then this is going to do this two more times as well. So I'm going to erase everything and let the computer generate a beautiful, clean picture. So as mentioned, this R group goes on with the same stereochemistry we had before. This is back to being trigonal planar. This OH is free to go off and do what it wants to do. Happens two more times so that now these two R's also go on to OR. So these three groups all have what we need. OH minus can attack. And then you have 4 on there, easily that OR can leave and end up with OR minus, which gets readily protonated in the environment. So in this reaction, we are going to add a boron first as a placeholder and then replace it through peroxide addition, peroxide substitution, I should say, and a rearrangement reaction to turn where the boron went into where OH finishes. So again, keep in mind, syn addition because they add at the same time at the same phase, and you retain the syn addition in this rearrangement. And then antimarkovnikov, the first uh, reaction of boron for the BH3, it's selective, but not highly selective. But the second and third one becomes significantly more selective. So if you want to emphasize or maximize your antimarkovnikov product, you need to make sure you add three alkenes for every one BH3. It's critical to this reaction. Okay, so building your own spider chart. So getting back to spider chart that we already started with, H2SO4 or any strong acid with water will form a Markovnikov hydroxyl group. HBr and shows CCl4, but we'll look at other potential solvents as we go. But for now, the one in aprotic nonpolar solvent will add the same thing, H on one side, Br on the other, Markovnikov. Now we're going to add BH3 and THF, you want to make note, is an ether. So I could put ether, E2O2, THF, whatever it may be. The second step, the peroxide, has to be done under basic conditions. Peroxides are oxidative. It's going to oxidize the boro carbon bond into a carbon oxygen bond and a boron oxygen bond. So you get antimarkovnikov, OH goes to the less crowded side, and H and OH add both either in back or both in front. Syn addition, stereoselectivity, antimarkovnikov regioselectivity. Okay, one more stereospecific addition reaction. This one's going to be a little bit easier to comprehend, but again, if the two substituents adding to double bond add at the same time, they add in a synonymous or syn fashion. So both H's add simultaneously, so they both add from the same side, either both on top or both on bottom. Again, we get no chiral center, so we can't verify it here, but it does work this way. No regioselectivity considered because H and H are the same thing, so an H on either side, H goes where H isn't, H goes where H is, because H is going to both. But it is important that we do the stereoselectivity. So no regioselectivity for this one. The stereoselectivity, syn addition. This one, it's just so much easier to visualize than it is to try to describe. But you use this on palladium, and I'm going to emphasize that when you see this, you're going to see carbon. And that means the palladium has been electroplated onto the surface of a carbon network, a graphite network. You do this because the reaction occurs only on the surface. And so if you have a big chunk of palladium, you're wasting the palladium in the middle. And as expensive as it is, you don't want to do that. So we put palladium on the surface of carbon. We put this chunk of carbon in there. It can easily be fished out and used over and over again. Very expensive metal, so we want to be very careful with it. So we plate it out on the carbon. So the palladium surface, and you're going to hear me sometimes use nickel, cobalt, rhodium, platinum. Sometimes I'll talk about a different metal. All behave in the same sort of fashion. So palladium for this one, but I want to just say we do this with lots of different metals. Okay, so the H binds to the surface. So when I add H2 to the palladium metal, H2 gets coordinated onto the surface. So when the alkene comes in, it's going to come into the H-rich surface. When it does, these coordinated pi bonds can now interact with these H's. They add simultaneously. So syn addition, because they align, they're going to pick up these two H's. There they are. And then fly off with their H's. The double bond is no longer there. I draw it this way out of laziness, but this is going to rehybridize and turn into something that looks like that. So those are now bonds to H. Syn addition adds at the same side. So this one, not much to it. That's pretty much it. We could use deuterium if we wanted to, so different isotope of hydrogen, but it's just an H2 reaction. We don't really do it with any other element. So one more for our chart, H2 and PT. If you're taking a test, let's say for this class or in the future for a different class, and you come across H2 and PD, Just keep in mind, we sometimes switch out metals for a whole bunch of reasons. Maybe it carries out the reaction a little differently, and I need that difference, or maybe it's just cost effectiveness. It's just cheaper at one point to use one metal and than another. And so there's many reasons, but don't get locked into exactly what's going on here. H2 and a metal catalyst, that's what matters. But you end up getting syn addition, and we don't worry about Markov-Cover, anti-Markov-Cover because we're adding the same thing to both sides. So, two more reactions down on our spider chart, and that's essentially what we're going to keep doing. We're going to keep piling on our spider chart. So, we're reached a point of being done yet again. So, have a wonderful time, and I hopefully will see you at the next podcast. Bye.